Yes, welcome back from first. Still, we are going to base our discussion on this zinc copper electrochemical cell. That is what we are going to base our discussion on. And based on that, we have said that an electrochemical cell is a combination of two or half cells which generate electric current as a result of redox reactions. And we give the example of zinc copper electrochemical cell, or we call it voltaic cell. Now, moving forward, so in this case we have said the half cell on the left consists of zinc electron immersed in zinc sulfate, and the one on the right consists of copper electron immersed in copper 2 sulfate solution. So we have two half cells. Now the electrons are connected by a conducting wire. We had seen that in our last video. And then the two solutions, these two solutions are normally connected with what we call a salt bridge. This is a salt bridge. Meaning a bridge is supposed to bridge the gap, bridge the two solutions, but it is made up of salt. Call it salt bridge. The salt bridge can be made of sodium chloride or even potassium chloride. Then down here we say we have the cotton. Now, so we said that before the two half cells are connected, we'll have electrons building up on the zinc electron and electrons building up on the copper electron. So before the two half cells are connected, each of them builds up a layer of electrons around it. Then the electrons will flow through the conducting wire. But then we have more electrons on the zinc because it is more reactive, and less electron on the copper. So electrons will move from higher electron pressure to the lower electron pressure. So that is how the electrons normally move. So once the half cells are connected, electrons flow from the electron with higher electron pressure, higher tendency to lose electrons. Zinc has a higher tendency to lose electrons than copper. So electrons will move from zinc to copper. Now another thing, the electrons are lost at the anode and they are accepted at the cathode. Oxidation occurs at the anode, induction occurs at the cathode. So from today onwards, you should define an anode as the electrode where oxidation takes place, and the cathode as the electrode where reduction takes place, gain of electron. So the zinc electrode, this electrode will dissolve gradually, while copper will be deposited on the surface of the copper electrode. The mass of zinc will therefore decrease, while the mass of copper will increase. Now, then we get the two equations of the zinc half cell, that is the zinc electron equation. Zinc losing electrons to form, and then on this side, the copper 2 will get electrons. So here we say zinc forming zinc 2 by losing electrons. Here we have copper gaining electrons to form copper solid. That is what we say. And This is the copper electron half equation. Then we have the overall equation. We looked at that. So, if zinc is the one that loses zinc electron, so zinc here becomes the reducing agent. Why? Because it is the one that loses electrons. And on this side, copper 2 becomes the oxidizing agent. Why? Because copper 2 gains electron. An oxidizing agent gains electron, while a reducing agent loses electron. Now, the flow of electrons will result in an electric current whose magnitude, meaning whose size, is equal to the electron potential of the half cells. So whatever will be recorded here by the number of voltage recorded here will be as a result of the flow of electrons. Whenever electrons flow, there is also flow of electric current. But now, the magnitude of the voltage recorded here will be equivalent to the electron potential of the half cells. Now, this value obtained is the electron potential of the two half cells. So what is obtained here is the electron potential of the two cells. Now, let's use another example, and in that case, our second example is magnesium and copper half cells. So let's rub this. Then, so if you did not get that properly, I'm going to use this to explain everything again so that you can get the concepts. So this is whatever the most reactive one should be on the left, the anode, where electrons are lost. So this is magnesium solid dipped into a solution. While on this side we have copper solid. Then we connect them using a conducting wire and a voltmeter. Then we connect the two solutions using a salt bridge. So this is our salt bridge. Inside the salt bridge we can place potassium chloride solution, and we block these two ends using a cotton wool. This one will be a solution that contains magnesium ions. This one is a solution that contains copper 2 ions. And we said when you want to measure the electron potentials, the molarity of these two solutions will be what? 1 molar. The temperature, 25 degrees Celsius. Now let's see the reactions. Magnesium will lose electrons to form magnesium what? Ions. Solid, aqueous. Loss of electron is what we call oxidation process. So this is oxidation half equation for this cell. Right. Electrons will move that way. These electrons will flow through the conducting wire. When they reach here, we have copper 2. So the copper 2 ions will gain electrons to form copper solid. Gain of electron is reduction. Okay? So the electrode where oxidation takes place, loss of electron, is the anode. So this one is the anode. The anode is negative because it has a large number of electrons, negatively charged electrons. The cathode here, this is our cathode, and the cathode is positive. The cathode is positive. So electrons flow from the anode to the cathode. Oxidation occurs at the anode. Reduction occurs at the cathode. We can combine the two half cells. So if you want to combine the two half cells, if we combine the two half cells, so that is the diagram that we have. Okay. So we have said the magnesium rod ionizes, dissolving to form magnesium ions at the negative terminal. That is the equation that we have shown there. Magnesium rod ionizes, then dissolving. That is what we have shown. Then the copper ions in solution gain electrons, gain the donated electrons to form copper atoms, to form copper atoms or copper metal. The equation is here. Then let us come up with the overall redox equation. We say that for the overall redox equation, we are going to combine the two. So we take on the reactant side overall redox equation. The reactant here is magnesium. The reactant on this side is copper. We collect the reactants together. Copper and 2 electrons. Then on the product hand side, magnesium ion plus 2 electrons. Then on the product here, we have copper plus copper solid. So electron will cancel electrons. We remain with magnesium plus copper 2 to give magnesium ion plus copper solid. This one is the overall redox equation. The overall redox equation for that magnesium, copper, magnesium copper electrochemical cell. So we should note that the anode, the anode is the electron where oxidation or release of electrons takes place. Anode is the electrode where oxidation or release of electrons takes place. And then the cathode is the electrode where reduction or gain of electrons takes place. Now, it is advisable always to draw the anode on the left and the cathode on the right hand side, so that electrons flow from the anode to the cathode. Those two points are very important. So we are saying that the anode is the negative electrode because it has an excess of electrons. It has more electrons than Now, the cathode is the positive electrode because it has an excess of positive ions. It has an excess of positive ions, meaning it has fewer electrons. Those are the reasons why those two electrodes have got those charges. Now, in electrolytic cells, this one I had mentioned it, and it's a very important point. In electrolytic cells, the anode is positive because it is connected to the positive terminal of the battery. Yes, I want class to compare. Let me run this. Because we need to travel back in time where in Form 2 we had something like this. Yes, this one is an electrolytic cell. Don't confuse it with the electrochemical cell. Now, in an electrolytic cell, this side, the long one, is the positive terminal of the battery. The short one is the negative terminal of the battery. Anything connected to the negative terminal becomes negatively charged. So, this one is the cathode. The one connected to the positive terminal is the anode. But look at this. Anything connected to the positive is positive. Anything connected to the negative terminal is negative. Now let us compare it with the electrochemical cell. In the electrochemical cell, the anode is negative. In the electrolytic cell, the anode is positive because it is connected to the positive terminal. That is what we are saying there. That in electrolytic cells, the anode is positive because it is connected to the positive terminal of the battery. While the cathode is negative because it is connected to the negative terminal of the battery. It is the opposite here, where the cathode is positive. So those 2 points are very important. Why the cathode is negative? Because it is connected to the negative terminal of the battery. Now, in electrolytic cells, the flow of electrical energy results into chemical reactions in the electrolyte, while in the electrochemical cells, the chemical reactions at the two electrodes result into the flow of electric current. Let me simplify that. You see, if we had a switch here, and let's say here again we have a switch. Let's start down here. Before we close the switch, nothing will happen here. If this one was molten, let's say this one was molten copper 2 chloride in liquid state, where we have copper 2 ions and chloride ions. Immediately we close the circuit, we complete the circuit, there will be flow of electric current from this battery. Electric current will start to flow. Then what will happen? If the electric current will flow, then this one will become positive and this one will become negative. The positive copper 2 will migrate to the cathode. The negative chloride will migrate to the anode. Then chlorine, chloride ions. Chloride ions will lose electrons to form chlorine gas. So what will be seen here will be chlorine, green, yellow chlorine gas produced at the anode. Green, yellow chlorine gas. See a green, yellow gas coming out. Here, on this side, copper 2 will gain electrons to form copper. So these electrons lost by chlorine, the electrons will move from the anode to the cathode. When they reach here, the electrons will be gained by copper 2 to form copper. So copper will be deposited at the cathode. Now, in summary, here it is the electric current that brings about chemical reactions. Electric current that brings about chemical reactions. But what about here? Here it is the reactions at the electrons. Reactions at the electrons that will bring about the flow of electric current. For electric current to be recorded here, from voltage to be recorded here, there must be a chemical reaction at the anode and at the cathode. That has to be a very big difference. That here, it is the chemical reactions to give the flow of electricity. Chemical reactions giving birth to electric current. Here, it is the electric current that brings about the flow, electric current that brings about chemical changes. For chemical changes to occur at the anode and the cathode in the electrolytic cell, electric current must be allowed to flow through the electrolyte. Here, the electrolytes must react, must undergo chemical changes for us to record a voltage in the electrochemical cell. Going back to that, now these statements can be understood that in electrolytic cells, the flow of electrical energy results into chemical reactions. While in the electrochemical cells, the chemical reactions at the two electrodes result into the flow of electric current. That one is a very important difference between the two. Now, finally, let us look at the functions of the salt bridge. Before we stop, look at the functions of the salt bridge. Now, this thing is called a salt bridge. And one of the functions of the salt bridge is it completes the circuit by allowing the contact between the two solutions. It is the one that completes this circuit. By completing that, by connecting the two solutions. Otherwise, there will be a gap here. Electricity cannot flow if there's a gap. That's one. Two, it maintains balance of charges or balance of ions on both half cells. It will balance the ions in both half cells. How? That's a very important thing to understand. In this salt bridge, I want to make it bigger. In this salt bridge, inside here we have potassium ions and chloride ions. Hundreds of them, not just one. Look at what is happening here. Here, this magnesium solid, you have said the magnesium solid is forming magnesium what? Ions. Where does the ions go? These positive ions, they move into the solution. So what happens to the number of magnesium ions? The number of magnesium ions will increase. If this thing was magnesium sulfate, and this one is also copper 2 sulfate, the sulfate ions will remain because we have magnesium ions and sulfate ions. Two positive charges, two negative charges. Neutrality. Electrical neutrality must be maintained in the two half cells. If we increase more magnesium ions without increasing the sulfate ions, the negative ions, there will be an imbalance. To maintain that neutrality, the chloride ions, which are negative, will come in. So the chloride ions will move in to increase the number of negative charges, so that we have equal number of positive and negative. This rod dissolves to give magnesium ions. So the number of magnesium ions will go up. To balance the excess positive charges, chloride ions will diffuse, because chloride ions are negative. So the chloride ions will diffuse into this electrolyte to create a balance, what we call electrical neutrality. Equal number of positive charges and negative charges here. What about here? Here, the copper 2, these electrons will flow. When they reach here, they will begin by copper 2 to form copper. So what will happen if we had copper 2 sulfate? If what we have here is copper 2 sulfate solution, if we had copper 2 sulfate solution, copper 2 sulfate, let me write in form of ions, then this copper 2 are being used up. If copper 2 are being used up, their number will go down, lower than the number of negative sulfate. So there will be an imbalance in this electrolyte, which cannot take place. To ensure that we have the same number of positive charges as negative charges, then as copper is being used up, then the potassium ions will now diffuse into the solution. So that as the number of copper 2 ions are decreasing, the number of potassium ions will increase inside this solution, maintaining the number of positive charges. So it maintains balance of the charges or ions on both the half cells. So next time when we meet, we look at electromotive force. Don't forget what we have learned about the functions of the salt pitch, the differences between electrochemical cell and electrolytic cell. Don't forget that the anode must be on the left, the cathode on the right. And don't forget that the anode is negative in the electrochemical cell, but positive in the electrolytic cell. The anode in the electrochemical cell is the cathode. In the electrochemical cell is positive, while the cathode in the electrolytic cell is negative. Don't also forget that at the anode, oxidation takes place, loss of electrons. The electrons flow towards the cathode, where reduction takes place. Otherwise, let us stop there. Thank you for listening.